Okay, so as we begin today, what was going to be on our schedule was start talking about the disaccharides, which, as we maybe briefly introduced in class, it is taking two monosaccharides. Now, whether it could be as simple as two glucose monomers or monosaccharides, you link them together, and maybe it's cellobiose. That's a different type of disaccharide as opposed to maltose, and lactose is another disaccharide. Now, with a lot of these disaccharides that we're referring to, it's not that we take those types of sugars in. An exception to that would be that of sucrose, which we'll introduce later on, perhaps tomorrow, as a linkage of glucose and fructose put together. But a lot of the disaccharides that take place in our diet, it's from breaking those materials down from our diet, and our major sources of sugar, of course, are going to be starch and cellulose. And I think a lot of you had mentioned that one of the things we really enjoy having is pasta. And of course, with that, pasta is a major source of glucose in the form of starch. And when that breaks down, now, does that give us lactose? Does it give us glucose? Does it give us maltose? Well, depending upon what enzymes actually secreted and actually breaks that content down. For those of you who have had anatomy and physiology, when we start in the fall, we start talking about the digestive system. And if we're talking about the sugar amylose, okay, that would be from the breakdown of the enzyme amylase and different types of starches, which could be in our diet of potato chips, again, that pasta, anything that would have a large content of starch in. That amylase then, of course, as we know, is secreted in the mouth by your salivary glands. And then another source is in your pancreas, which then injects that in your small intestine. And that's how those really large, complex molecules are broken down in our body so we can actually utilize those. So we're going to make a reference to your first paper, and that would be the one that looks like this, okay? And it has all these, I don't know how well you can see this. I know we have different aspects that we're trying to bring this light from below. We're all familiar with this. Maybe it puts a shadow on there, but I think the last thing we want to do is have a light on in the back, and then of course that puts a couple of glares on there. So the disaccharides, if you had brought a textbook home, or if you chose to do so, begins on talking about those on page 547 and gives you examples on page 548. So what we want to do, for instance, is as we look at this paper, on your first assignment is, I see on number 4. We'll just go ahead and utilize that as an example. And let's say, for instance, can we hook those together in a specific type of linkage? That'll come later on in this, if you want to call it a presentation or illustration, whichever. I'm trying to, so I'll put these markers over here. Some of these are probably still from a couple years ago, and these markers just dry out. So hopefully these new ones that I brought from the school will actually show up. Okay, so again, number 4 on your paper is we see if you follow directions, we know that's an aldose sugar because that double bond oxygen is on carbon number 1. We know that it is a hexose because it's got 6 carbons, and then we didn't have to give the specific name of that. So what we are going to do here, okay, there is our, let's see here, I want to see, that's not showing up very well, is it? Okay, so I think we need to stick with the darker, maybe just plain black and brown. Maybe we'll just use black only. I think this will probably show up a little better. Yeah, I think that's better. Okay. All right. Need to make a little space here. Okay. And then our orientations on here, I think we're, what was it? right, right, left, right. Okay, and then here's our bottom down here. And you'll probably notice that on a lot of these papers I don't put those hydrogens in, which is, of course, no big deal, because the OH atoms on here are the most important to actually have. We tip this over on its side, remember, and by now I think we perhaps have a pretty good grasp on this. Of course, that's how it starts out. There is carbon number 1 right here, and going around the bend all the way to carbon number 6. Okay, so we'll say that these have already switched and flipped. Because remember, when we say switch, this guy is way out here on the end, down here in carbon number 6, and that switches with carbon number 5. Okay, we've got right, so that's down. We've got right, so that is down. Okay, on carbon number 3. And then carbon number 4 left, so that's got to be up. Okay, and then remember, this has an OH down here, and then the hydrogen's up there. So when we're talking about this switching and flipping, okay, we're going to close this ring. These two switch, and then the hydrogen flips at the same time. Okay, now where's my eraser go? Right here. So we're going to go ahead and switch these, and then flip them. Okay, so we've got CH2OH up here. Here's our hydrogen, and then OH way out here on the end, because it had switched and flipped at the same time. So now what we're going to do, just a moment, I hear my phone ringing. Okay, and then as we know, this hydrogen comes down here and breaks that double bond, and then that's why it's known as a reducing sugar, which all of these are. So we'll go ahead and close this ring now, and since that's on the bottom, we'll just go ahead and keep this as a beta molecule, because that OH then would be on top. Okay, so again, that's how we close that ring. And a lot of you probably have that done already, which you didn't have to do this for problem number 4, but just again, as a quick review on how to close those rings. So as we look together at, if you have a book on page 548, what happens is you will take 2 monomers. In this case, we'll just keep it simple with that of glucose, because we know that glucose molecules do hook together. It's the manner that they will link together that's going to be different from other types of disaccharides. So in this case, some of you might not have to go back to these Fisher projection formulas. What we can do, okay, oops, I didn't mean to do that. What did I do with that eraser now? Okay, I meant to leave this space here. Okay, just, getting better at drawing these 6-sided figures. We'll just go ahead and make these as 2 alpha glucose molecules. Okay, so what that means then, it's already predetermined, since this is alpha D glucose, we know that this is down. That OH molecule there is down. Okay, and then of course we remember our orientations, which is right, left, right, right. So right is down. Again, this is a different monosaccharide. This was a prior example. Okay, so right, left, right, and this would have been right, but we've already done the flip and the switch. Okay, so here is glucose. Okay, so I'll just abbreviate that inside of there as glucose. So if we take another glucose molecule, okay, and we'll just put it right next to here. We'll start with this oxygen, okay? Didn't make it as big as that last one. I'll make that a little bigger. Okay, so we can actually see it. Okay, not quite as big, but that's okay. So this is already predetermined to be glucose, and we'll just go ahead and put that as the same as an alpha D glucose. Okay, so right, left, right, and this was right, but again, we did the flip and switch already. Okay, so we got our two glucose molecules here side by side, because glucose is rather unique because you can link two of these together, a monosaccharide and a monosaccharide, to make, of course, as you would picture, a disaccharide. And the key to this is when we start linking these together, okay, when we see this, okay, and it's in parentheses perhaps as 1 and 4, that's a very common linkage, and then beta 1, 4 is another common linkage. So what these are referring to is the carbons on these ring structures, okay? So perhaps what gets to be maybe a little confusing is read this from left to right, okay? So left and right, we've got our two glucose molecules together, and we're gonna link them, okay? And in order to do that, it has to go through dehydration. And if you remember from probably last, I don't know, probably October, maybe November, one of the things we had said, it's always been about the water when it came to that of organic chemistry, and we know that it's all about the water with that of biochemistry here, because when we're looking at the Percy Julian project, okay, one of the things that happened with the production of stigmasterol is it was just simple water that causes that to precipitate out in an oil in the formation of stigmasterol, okay? So again, water is such a very unique compound. And in this case, if we are going to read this left to right, which we will do, it's just simple as here's 1, okay? Here's carbon number 1, and of course here's carbon number 4. So that's what that's referring to in a 1,4 linkage, okay? Then as you would note, that when we drew this, okay, it's alpha D glucose, okay? This one is also alpha D glucose. So what we see happening then is if we're going to link these two together, some intermolecular dehydration has to take place. And in that instance, here's carbon number 1, and here's carbon number 4 when we're reading that left to right. And that's what we're referring to here. Here's our left, here's our right one. So on carbon number 1, here's our OH molecule, and on carbon number 4, our other OH molecule. So what's going to happen is we're going to take water out of there. And we want you to do that in a specific manner, because when we did that with our esterification process, if we had, let's see here, we'll keep this as simple as possible. That's one of the problems with this. I just don't have a whole lot of room here. We're adding then ethanoic acid and some, you could say just some ethanol, okay? We said it's all about the water, that we want you to do this in a specific manner, okay? So what happens is this gets stripped off of there, that OH, and then this hydrogen. There's our water. So then when we link those together, okay, here's that oxygen down here, here's our other two carbons, okay? Our double bonded oxygen is still there, and there's our process of esterification. There's our double bonded oxygen, so therefore we've got ethyl ethanoate. Okay, so in this case, what we want you to do is something very similar. Show how this is going to go through the process of dehydration, very much so how you've already illustrated that with esterification. So what we would do then, okay, the clue that we want you to perhaps remember from here going forward is we don't want you to be left behind. That's your clue, okay? When we say we don't want you to be left behind, okay, that means this OH molecule comes off, okay? And then here's our other half, this hydrogen. So then that leaves our single oxygen, just like it does in esterification on that alcohol. So here's our lone oxygen, and that's where the linkage is going to take place between carbons number 1 and carbons number 4. And since it's an alpha linkage, that's going to be oriented downwards. So I'm going to erase that, and we're going to link those together. So now this OH molecule, whether you could say it's hydrolyzed or whether it's something that the body takes all those all those glucose molecules and starts putting them together, it goes through a specific process and is going to link these together into a disaccharide now. So we had just that lone oxygen. Now they are linked together in an alpha 1,4 linkage. Again, carbon 1, carbon 4, and that's how they're linked together. Since it's alpha, it's pointing down. Because if it was a beta 1,4 linkage, that means this would have to be up a little further and still carbon number 1 and carbon number 4, but what that means is this would have to be sitting up top here, a little further up. It can do that, but once you change that linkage, okay, it's going to be a different disaccharide. Because once we link these two together, if I'm remembering correctly, this would be maltose, I believe. Yes. Okay. So when we do that, that is, again, maltose. So now we've got, this is down here, so we've got alpha-D maltose. Okay. That's a disaccharide, 2 monosaccharides bonded together. Okay. And that's how you go through the process of linking these together. Be able to illustrate how that dehydration takes place and how to link them together. Okay? Because if we did a beta 1,4, we can illustrate that at a later time. We're up to 18 minutes, and I see that's probably, again, we try to keep these presentations between 15 and 20 minutes. If we did a beta 1,4 linkage, it wouldn't be maltose anymore, it would be cellobiose instead. Okay, so some of these problems we'll go through and say, for instance, if possible, link these together in an alpha 1,4 linkage. If possible, link them in a beta 1,4 linkage. So one of the reasons we wanted to leave this here, okay, whichever monosaccharide that was, just hang on for just a moment. So this one is actually gulose, okay? The monosaccharide gulose, so I'll put a GU there. This one's glucose, here we got gulose. So would this be possible to link in an alpha 1,4 linkage? I want you to think about that for just a moment. We're talking about gulose here now. Would this be possible to link together in a disaccharide? So after hitting pause, I thought I'd give you a little bit of time to maybe spatially visualize that. In order to answer that, we don't have to erase this whole structure. We're going to change it. Okay, so that's still the same. That's actually down. Okay, so this one is hydrogen. That's OH. Okay, and then if we do this where it's switched, that is hydrogen, and that is OH. Okay, so again, this is gulose. if you were to link these together in an alpha 1,4 linkage, if this started out like this, yes, that would be possible, okay? Because we still have our OH molecule here, we had our OH molecule down here. But if we were to put this one over here, could we do 2 gulose molecules? Okay, so we'll illustrate this how it should have looked. Okay, so then OH is down here, and then we have hydrogen and OH up there. So as you're looking at this, would this be possible to link together? And of course the answer to that is no, because we don't have an OH molecule down here. So that's why sometimes what it might say, it can be possible, sometimes it's not possible, depending upon how you're trying to link those together. It might be hard to wrap your head around that, but this will become more clear and easier to maybe comprehend if you want to look at it that way. And the reason that this might be a little difficult at this time is you got to remember, you haven't spent a lot of time on this, and unfortunately Mother Nature has decided to push all this snow upon us, so I think that's probably enough for today. I was going to try to look at some specific questions about on worksheet 2, but we'll make reference to that tomorrow. I just wanted to illustrate what a disaccharide was and how you actually link those together. So will we be in session on Friday? Good question. We can only keep our fingers crossed. We're just doing the best we can to get us through this content. That's all I have. We will tune in next time for some more fun, if we want to believe that, I hope. Anyway, thanks for taking the opportunity to tune in, and again, we'll catch up to you next time.